Hello children, in this video we will be discussing the entire chapter of sound. Children, this chapter has two units. So all concepts from this unit A and unit B will be covered in this video. So children, let us see what actually the concepts which we are going to cover in this video. That is, what is the today's agenda. Children, first we discuss the concept of sound. There we discuss the very important bell jar experiment. There only we discuss the, of course, after that only we discuss the properties of the medium. Children, of course, which we will be discussing that sound requires a material medium. So then, as sound requires a material medium, children, it should have some properties. So those properties we will be discussed. And after that, we discuss the propagation of sound. After that, the most important wave concept which will be discussed. There only types of waves, the terms related to the waves also will be discussed. And after that, we will be discussing the speed of sound. Especially children, examination point of view, the factors on which speed of sound depends, the factors on which speed of sound does not depend also very important. And the comparison between sound waves and the light waves. Finally, we will be discussing the properties of the ultrasonics and their applications. So children, these are the important concepts of course, today's class. And children, as usual, every time I will tell you the very important thing. What is that, children? Yes, you may refer any video or you may refer any guide. The important thing is that you should go through the textbook. So referring the textbook is a mandatory. So after that only these videos and the material it's a second thing actually. The first thing, the primary thing, what we have to do, we have to read the textbook, and after that children, just go through the exercise questions. And one more very important thing, children, here, we have to do one important thing when reading the textbook. What is that here? Whenever we read a textbook, children, just keep our notebook with you, so that whenever we are reading a textbook, definitely we may get some doubts or some terms may not be clear to us. So if you can note down in a particular in a notebook, so that you can discuss with your teacher, or even you can discuss with your friends also. Of course, if you are regularly watching our videos, you can comment in in any videos also, so that your doubts will get clarified. Okay children, fine. So okay, before getting to the what actually sound, children, here I have a very small question here, very important. Sometimes some will underestimate a question. So this question is that type only. So children, we know about wet air and dry air. I mean, which one is whose density is more? Either wet air density is more or dry air density is more. So children, just pause the video, think about it, and comment your answer. Just you see, don't think whether whatever the answer which you are going to comment is right or wrong. It's not that. Just you think according to you, according to your knowledge. So previously, we might be having some knowledge, or somewhere we might be heard about dry air and wet air actually. Just think about it. So it's a very important. Okay, commented your answer? Yes. So if you want to know about the answer, and if you want a clarity, if you want to know the what we can say, what actually the answer is, whether dry air is heavier or wet air is heavier, you have to watch the video. Then definitely in between we'll be discussing about this, so that we'll get a clarity. Okay. So children, first let us discuss what actually sound is. Children, is this sound new to all of us? No, it is not that. So from morning to, the moment when we get up from a bed to the moment when we go to the bed, children, we can come across with many sounds, in which useful sounds will be there, some useless sounds will be there. That's quite natural it is. Children, can you imagine how the life would be if there is no sound? Many people, some people will think that, sir, if there is no sound, so very cool and calm you think. But children, very important thing. If sound is not there, just you can't imagine the situation also, because that is it's horrible. Just think about the situation where you are in a big house and there is no person, and moreover there is no sound. How it will be? It will be more scary, So it's a very horrible. So the problem is that if sound is not there, problem only, and if sound is there more and more also, it's problem only. Okay, now fine. So same question, still I remembered, I think a few years back, I asked this sound, so-called student Mahesh, still I remembered, I asked, what is the sound? Then he got up and he did like this. And he said that, sir, this is called sound. I was surprised to say whether it's the right answer or wrong answer. For a while, I was thinking, what I asked about sound only. What Mahesh did? Yes, he made sound and he said that this is called sound. It's right only. And nowadays the students are more practical oriented. They want to do the things and they want to learn. Of course, then Mahesh, absolutely he was right only. That's correct only. But in exam, if the question is asked, we can't do like that, right? So what is a sound, children? So simply look at you, children. So whatever we are thinking about sound, children, yes, it is like light. Sound is a form of energy. Children, it's very, very important. Sound is a form of energy and which produces sensation of hearing in us. Children, these terms are very, very technical terms are very, very important. We have to learn. So which produces sensation of hearing in us, sensation of hearing in us. And here sound is produced by vibrating bodies. Sound is produced by vibrating bodies. Sound is produced by vibrating bodies. The very, very important. Means what? All vibrating bodies can produce a sound. What is the evidence, children? What is the evidence? And you may ask one question, sir, how can you prove that vibrating bodies can produce sound? Very simple. So right now, children, all can hold your throats. Okay, na? Are you holding your throats? Means don't hold tightly. Okay, it's not that. Okay, na? So there will be a problem. Just normally, just you can hold it and try to make a sound. What kind of sound? You may sing a song also. It's not a problem. Yeah, let us read about this only, right? And by holding this sensitively, by holding throat sensitively, let us talk about this. Sound is a form of energy. Okay, which produces sensation of hearing in us and which is produced by vibrating bodies. Children, when you are reading, are you able to feel some vibrations? Obviously. So, this is what actually, children, physics is a very easy. The moment when you can notice the things which are happening, nothing will be there to learn actually. Okay, na? Just observe and you can learn. So, sound is a form of energy which produces sensation of hearing in us and which is produced by vibrating bodies. But the very important thing is that, children, can we hear the sounds produced by all vibrating bodies? Children, no doubt about it, all vibrating bodies can produce sound. But my question is that, can we hear the sounds produced by all vibrating bodies? Just pause the video, think about it and comment your answer. Can we hear the sounds produced by all vibrating bodies? Yes or no? Just pause the video, comment your answer. If possible, you can give example also. You can give example where bodies can vibrate but we can't hear the sound. So about this, children, the clarity will be, you will get the clarity at the end of this. End means not last 1 or 2 minutes, just, last 10 minutes, we'll be discussing about this only in detail. Am I clear, children? Fine. And here, sound, we know that matter can exist in 3 states: solids, liquids and gases. Obviously. So obviously, children, here sound can travel through the solids, sound can travel through the liquids and even sounds can travel through the gases. But the question is that in which medium sound can travel faster? It's very important. Children, example let me give you. So let us take a granite here. The very important examination point of view. It is a granite, let me take, and water. It's mostly sea water we'll be discussing. Then let us take air. So children, this is solid, this comes under liquid and here is gas, no doubt about it. Okay, now fine. So children, through the granite, the speed of the sound, experimentally it has been proved that 6000 meter per second, whereas through the water it is approximately 1450 meter per second, whereas through air, children, it is 330 meter per second. So with this, it's a very clear that sound can travel faster in a solids, slower in a air. That is what in a gases. Okay, children, this is a very, very important. Okay, so with this it's very clear. Okay, sound can travel through the solids, sound can travel through the liquids, sound can travel through the gases. But the question is that, can the sound travel through the Vacuum. Children, this is most wanted. So actually, if you want to understand whether it can travel through the vacuum or not, we should understand the nature of the sound, children. This is very important actually. If you want to understand the nature of the sound, we must understand a wave nature. So wave concept is very important. Okay, so this everything, in a sequence manner will be discussed, not to worry about it. Okay, na? So can sound travel through vacuum or not? Yes, obviously sound cannot travel through the vacuum. But children, what can we give an example? Do we have any natural examples? Natural examples means, yes, we have a natural example. What is that natural example? Children, in a space, many explosions are happening. Many explosions are happening actually. So without, horrible sounds are produced. Are we able to hear? No. Children, if we would hear, definitely we wouldn't be alive actually. Such a horrible sounds. So we are not able to hear the sounds which are produced from the many explosions which are happening in a space. The main reason is that, children, after a certain height, there won't be any atmosphere. Complete space it will be there. Complete vacuum it is there. So through that, sound is not traveling. That's the best natural examples to say that sound cannot travel through the vacuum. But practically, how can we prove that sound cannot travel through the vacuum? Children, for that only, the best experiment setup which we have is a bell jar experiment. Children, even some 6th, 7th standards also, you might have learned about it, but nothing is wrong in it. Just let us recall once again. So children, let us see actually what is the arrangement setup. It's very simple. It's like it's a jar. Okay, na? So this bottom of this jar is removed and it is replaced with a vacuum pump. Okay, into this glass jar somehow what we can say, electric bell is introduced, and it is a rubber cork. It's an airtight rubber cork, children, so that air won't enter and air won't escape if it is present. Okay, na? And here it is connected to the what we can say, power supply. Children, many of you might have seen this in many schools. It will be there. For every 40 minutes or every 45 minutes, bell will be given, right? So that is what actually here. So it is a jar and here is a bell. So simple, it's a bell jar experiment. So what we have to do, children, initially, the moment when you can connect the circuit, when you switch on the circuit, what happens? Current passes through the circuit, and obviously, children, this is called hammer. It is called gong, metal gong. So the moment when current is passed through it, what happens? This hammer will be hitting the gong continuously. So what kind of sound is produced? Let us say I switched on. Did you hear the sound? Yes. That is what actually sound is produced. And here, after that, children, what we have to do? If you can switch on the vacuum pump, what is the importance, what is the role, what is the function of the vacuum pump? Vacuum pump can take out the air which is present in the jar actually. So the moment when you can on the vacuum pump, children, you can notice that, of course, let the bell ring continuously, simultaneously on the vacuum pump. Slowly, the air which is present inside the glass jar is being removed. So you can notice that, children. So initially, you can hear the sound in a loud manner. But as the air is being removed continuously, the whatever sound which we are able to hear, that gradually decreases. After certain time, though the hammer is hitting the gong continuously, so that this gong will be vibrating, but we can't hear the sound. The reason is that, children, the complete air is removed with this vacuum pump. Then what is left inside? Inside it is completely vacuum. Vacuum is created. Inside completely vacuum is created. So children, once again I am telling you, though hammer is hitting the gong and gong will be vibrating continuously. As there is no air, as vacuum is created, we can't hear the sound. So with this experiment, we can conclude that sound cannot travel through the vacuum. Children, this is a very important experimental. It's an experimental setup. It is actually. It means practically in a laboratory. This is the best example to prove that sound cannot travel through the vacuum. Okay, fine. Fine, children. Now we discuss the propagation and how the sound is propagated. So, children, sound is propagated in the form of wave actually. So, especially in air, children, sound can propagate in the form of longitudinal wave. So here one term, a new term is coming children. What is that? Wave. So children, now let us discuss what actual wave is, wave concept. Children, if we can understand wave concept and types of waves, then only we can understand it's very clearly, we'll get a command on the propagation of sound. Children, what is a wave children? It's very simple to understand. So again I'm telling you, just don't take any burden. Okay, just feel relaxed. It's very easy. We are going to make it very, very easy. So children, let us assume that or you can do right now also, you can get some water in a glass, just keep in front of you. If you want, you can do it. It's not a big task, so that we can have better understanding. So children, just let it be a water in a glass in front of you. Just wait some time. Sometime is not 1 hour, 2 hours. Let it calm. The water should be very calm. Okay now. And children, in that water, glass of water, try to touch the water, in middle part, try to touch with a finger. What happened? The moment when we touch that water surface with a finger, what will happen children? Yes, obviously, water will get disturbed. Water will get disturbed. Did you notice anything in that? Yes, we notice. Some circles like things are formed. Scientifically, we can call it as ripples. I mean what? Ripples are formed. My point is that just notice, observe that ripples children. The moment when you touch that water surface, ripples are formed. Do you think that ripples are sitting there only? Just think about it. Observe. No, ripples are not sitting there. What is happening? They are moving in all directions. They are spreading. Ripples are spreading in all directions. Ripples are spreading in all directions. Okay children. So then what we have done, what we did, we created a wave. Yes. And you are getting a one doubt actually. Sir, okay, I have taken a water. I disturb. Ripples are from. Where is that wave? Yes children. Scientifically, whatever the disturbance which we created in that water, only wave actually. Then what we did? We created a disturbance. Is that disturbance staying there only? No. It is distributing. It is traveling in all directions with equal speeds. That disturbance only we can call it as a wave. Children, even you can notice, you can just see the definition of wave on the board also. It's very important children. What is a wave? Examination point is very, very important. The disturbance created in the medium which can travel in all directions with equal speed is called wave. Fine children. The one more very important thing is that then during the propagation of it's very, very, very important. Very, very important. This is the main key point to get the command on the wave concept actually. What is that important point here? Children, during the propagation of wave, molecules of the medium do not move. My God, some of you may get confused. Sir, what is that? How it will happen like that? Yes children, that is true actually. So during the propagation of wave children, molecules of the medium, they do not move. Then what do they do sir? Yes, they will vibrate from their mean position. Molecules of the medium vibrate from their mean position. And children, one more thing actually. What is the main concept of wave? Concept of wave is what actually? One of the modes of transfer of energy. Wave is propagating means what children? It is carrying the energy. How it happens, then you make it one doubt. Sir, without a movement, as you are saying that molecules are not moving, but how the energy is carried? Children, to understand this, the best example, in a class only, children, let's just imagine situation. Here is one classroom, it is one row, let us take that here. Here one bench like this. Of course, you can notice in your class also. You can do it also. Let us say here, it's one bench. Let us say one student is there. One bench here. One student is there. Let us say here 1, 2, 3, 4. Total 6 students are there. 6 students are there. Just think that in that particular class, a teacher gave one object to this student A, asked to pass to the last student. Of course, for that, the best two options which we have, what is that? This student can take that object, can throw to last bench student. This is what actually mostly which will happen. See, whenever a teacher will turn back towards the board, so the things are flying in air, right? We should not do that actually. So that is one method, but we are not going to do it. The second method is what this option this student A has. He can just get up, he can walk, and he can give. That is the second option. but that is also not accepted. Children, can you think, is there any other method, is there another way where he can transfer piece of chalk? Getting idea? Yes. How, children? Just for example, children, I am the student, you think that. I am the student, I am a student A, student B, C, D, E, F. So you think that I am the student A. What I do? Just I will turn back, I will give to student B. Then what will happen? Again, after giving student B, this student A again will come back to his position. Then what student B will do? Again student B will give the thing to student C. Again will come back to his position. So this is how it can be carried to the student F also. Children, in this example, are the students moving? No, they are not moving. What they are doing? Just they are like vibrating. Like this, again they are coming. It's like a, kind of exercise, right? Of course, it's like, it's turning back, again coming to the position. Turning back and coming to their position. So this is what actually happens during the propagation of wave. So children, let us take it as a complete wave. These students are just you take like, it's molecules, the medium. So they are not, students are not moving. They are carrying this object. This is what actual energy. This is how energy is carried. Children, this is a very, very, very important point. During the propagation of wave, molecules of the medium, they do not move. Rather, they will vibrate from their mean positions. This is very important. Children, so depends on vibration, children. Depends on vibrations. Waves are grouped into two categories. How they are vibrating? Either they are vibrating parallel to the direction of propagation of wave or perpendicular to the direction of propagation of wave. So children, now we discuss the types of wave. Based on what, children? Based on vibration. How they are vibrating. How they are vibrating. So based on this actually, waves are classified into two groups. What is that first group? The first group is longitudinal wave. Children, it's very important. The first one is longitudinal wave. Longitudinal wave. The second one is transverse wave. Second one is transverse wave. Transverse wave. So it's very, very, very important. So children, just imagine a situation. Let us just take a situation where some people are standing in a queue. It might be for water, might be for milk. Previously we used to stand for movie tickets. Nowadays, of course, it's a completely online booking. Right, so we are not going to theaters to, yes. So when we are studying in a college, we used to bunk the college and we used to go to the movies, where we used to stand. So big row it would be there. Of course, no, we should not bunk the colleges and we should not bunk the colleges, right? Okay, that's fine. So just imagine a situation where students are standing, not students, some persons are standing in a row, in a queue. Persons are standing in a queue, just you think that. And in that situation, children, let us say like this, the persons are standing. So this much gap is not there, let us think. This much gap is not there. Okay, now fine, let us think. And it is, till here it is restricted so that no other persons can enter. This queue is completely filled, let us say that. Now sometimes what will happen, because of lack of patience, just think that this back person pushes this fellow, let us say. Then what will happen, children? All persons will go like this. Just you think that they do not have a chance to move. Again, I am telling, it's an assumption, right? We can think whatever we want. Just think that the persons, they do not have a chance to move. So in that situation, if a person give a push, then what will happen? Do you think that they will be jogging or they will be walking like this? No, it won't happen. Then simply, just you think that one person just gave a push at the back of me. Then what happened? Just, yes, like this. All persons, almost all persons will be like this. Then do you think that this friend fellow will have patience to bear it? No, obviously. Then he pushes back. Then what will happen? All will be pushed like this. So in this example, children, so they are pushed like this, like this. So what is happening? Just to think properly, as a push is given, so either they are bent forward or backward, forward or backward. Am I right? And strictly they are fixed to their position. Strictly they are fixed to their position. Either they are moved like this, bending forward or backward. Am I clear, children? So this is called actually to and fro motion. To and fro motion. Okay na? So means this is what exactly happens with the longitudinal wave. Which means what, dear children? Whenever longitudinal wave is propagating, the molecules of the medium vibrate parallel to the direction of propagation of wave. Children, it's very, very, very important. The molecules of the medium propagate parallel to the direction of propagation of wave. And in this, children, in this, so as I said that when push is given, then what will happen here? Persons may come very close to each other, very close to each other, very close as push is given. So this is area where density and pressure is maximum. Pressure and density is maximum. This region is called compressions. This region is called compression. So it's very, very important. The region of maximum density and maximum pressure is called compressions. When as a push is given, then what will happen back, children? Obviously, so when see, just you think, initially when push is given, almost all will bend forward, right? So that back what will happen, there will be some gap between the persons. There might be some gap actually. There might be some gap like this. So this is a region where density and pressure is minimum. So this region only we can call it as a rarefaction. Children, it is not a fraction. Faction. Now, faction is to move. It's a faction. Okay, now it's a rarefaction. So, which means what, dear children, here during the propagation of longitudinal wave, simultaneously compressions, rarefactions are formed. So, it's very, 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 very important. So, what is a longitudinal wave? Children, just imagine a situation. Unless and until you imagine a situation, children, just reading the definition again and again, it's too difficult. You may remember, but you can't understand. Just imagine a situation, what is happening here. See, it may not be exactly 100. I am not saying that this example is 100%. It's mostly. You might be having the best example. Yes, go ahead with that. I'm not saying that take this example and understand. No, you can take any example where you feel comfort, very easy to understand the concept. Am I clear? Fine. Let us recall once again. What is a longitudinal wave, children? The wave in which particles of the medium vibrate parallel to the direction of propagation of wave is called longitudinal wave. And the very important thing is that during the propagation of longitudinal wave, children, compressions, rarefactions are formed simultaneously. I mean what? Compression, rarefaction, compression, rarefaction, compression, rarefaction. And the best example, what is the best example for a longitudinal wave, children? The sound in air. Sound in air is the best example for longitudinal wave. And one more thing, dear children, longitudinal waves can travel in the solids, liquids and gases. Very, very, very important. Very, very important. Longitudinal waves can propagate through the solids, liquids and gases. Clear? Fine. Now, we discuss about a transverse wave. Transverse wave. So, children, recently, I visited one amusing park actually, where some children are playing. So, there would be a net. So, the name, I'm not able to recall the name of that. Where actually students were enjoying. Just, I'll tell you, if you can, get that to your mind, you can comment your answer so that I can read and I can learn that. Okay, now fine. So, there would be like this net is there. There would be net like this. Okay, now fine. So, there what happened, student. Not a student and child, let us take. Why always to take out student? Everyone is taking about a student only. It's not that. Let us take a student. What happened? Just they are jumping. Just they are going up like this. They are jumping like this. So, did you recall the name of this one actually? If so, you can comment your answer so that I can go through it, and definitely next time I will tell that what actually. Okay, fine. So, here what will happen, children? This child will go either up or down. Am I right? Either up or down. Am I right? Yes, yes. Hope you you can recall that what actually. So this is a situation where this particular student either he is moving up, down. But let us modify a little bit, and is okay. Is up down is happening, but just think that he is not leaving that net. That's very important, because when the medium is wave is propagating, molecules should not leave their positions. Actually, again, I'm telling you, it may not be 100% exam is suit to this situation, but mostly we can understand. Children, I'm just trying to give you an idea how the molecules will vibrate. My intention is to give you an idea how molecules will vibrate here. Let us think that this boy or a girl is in a molecule, so that vibrating how up and down. Children, wave is going like this. This is the direction of propagation of wave. It is a direction of propagation of wave. To this direction of propagation of wave, children, how this particular child is vibrating up and down, up and down. The resultant wave only we can call it as a transfer wave. Means in a transfer wave, children, how the molecules of the medium will vibrate up and down, which means what? Perpendicular to the direction of propagation of wave. Children, this is a very, 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 very important. Very, very important. What is a transfer wave? Children, whenever the definition is asked, just you recall how the molecules of the medium vibrate. Just don't by heart, children, please. Don't by heart. If you can by heart, chances are there to forget. If you can understand, to understand that, we have to imagine a situation. Just we have to imagine a situation. Transfer wave is going like this. Transfer wave is going like this. How the molecules are vibrating like this. Molecules are vibrating like this. Up and down, up, down, up, down, up, down. That is called perpendicular. So come on, let us tell the transfer wave definition. The wave in which, what you can say, the particles of the medium vibrate perpendicular to the direction of propagation of wave. Shall I repeat once again? The wave in which molecules of the medium vibrate perpendicular to the direction of propagation of wave is called transfer wave. So now we'll see how can we represent a wave. Children, I'll try to give you an idea. Just follow it. Let us think, children. This is how actually wave is propagated from left to right. Let us think. So children, here all molecules will be there on this. Let us say that this is a molecule. It may go up like this. This molecule may go up. This molecule may go, and one more molecule, it may go to from here. Children, this is a mean position. It may vibrate from here to here, and the next molecule. Children, just I am trying to show with a displacement till what maximum displacement they may go either up or down. Okay, fine. And this molecule may be down like this, and here like this, and these molecules might be like this. Just I am trying to show the direction, children. The direction. Just I am trying to show you the direction. Just imagine a situation, because in a transfer wave, as we discussed, that the molecules of the medium will vibrate perpendicular to the direction of propagation of wave. Children, if you can think here, just try to notice that. So these arrow marks, children, these arrow marks will represent the, what we can say, vibration from here to here. It may vibrate here. I mean, children, these things will happen simultaneously. Here, for a given instant of time, these molecules are vibrating like upward direction. These are downward direction. After some time, this will come down. This will go up. So this what it will be happening. This is very, very important. Children, just assume the situation. Imagine a situation. Imagine a situation. So here I am trying to show the displacements here actually. So this is the straight line. This is the direction of propagation of wave, and this is a mean position. From this mean position, either the molecules will vibrate up or down for an instant of time. Any instant of time, like this, they are vibrating. After some time, what will happen? Again, these will be coming down. This will be going up. So up and down, up and down. This is what actually happening. So it is simple. For sake of our convenient, we can represent like this actually. So this is how actually we can, this wave actually. Okay, so it will be continued like this. it will be continued. So this is how actually we can represent the best way about the transfer wave. So children, here if you can see, there are some particles. See, for example, let us say this is A, this is B, this is 3 particles I have taken. So this is a displacement of this particle A. This is a displacement of this particle A. This is a displacement of this particle B. Among these 3 particles, children, which one will have maximum displacement? Obviously, particle B. But this displacement is vertical upward direction. Upward direction. Let us take here D particle, E particle, F particle. This D, E, F particles also will have displacement but downward direction. This is very important. Very important. So children, this position of maximum displacement upward direction is called crust. Very important. Very important. Whereas the position of maximum displacement downward direction is called trough. T-R-O-U-G-H. Children, it is not tough. Don't say that, sir, physics is tough. No. Physics is not tough. I don't accept. We will make it tough actually. Okay, na? Fine. So children, it is what actually crust, and this is what actually trough. This is what actually trough. So during the propagation of transfer wave, children, crust and trough is formed. This is a trough. Again crust. Again here will get again trough. Am I clear, children? So this is how actually we can represent the transfer wave. We can represent the transfer. Water crust and water trough, children. The positions of children, either crust or trough, both are maximum displacements only. But what makes the difference? This crust is vertically upward. This trough is vertically downwards. Hope I am clear? Yes. Let us recall once again. What is a longitudinal wave, children? The wave in which the particles of the medium vibrate parallel to the direction of propagation of wave is called longitudinal wave. And the very important thing, again I am telling you, during the propagation of longitudinal wave, children, compression, rarefactions formed. And these longitudinal waves, children, they can propagate through the solids, liquids and gases. Very important. And the best example for a longitudinal wave is what actually? The sound waves in air can propagate in the form of longitudinal wave. That is the reason why I said before going to discuss about the propagation wave, children, it is a compulsory to us to understand the wave concept. Fine. What is a transfer wave? The wave in which the particles of the medium vibrate perpendicular to the direction of propagation of wave is called transfer wave. In a transfer wave, children, that is what, when transfer wave is propagating, crust and troughs are formed. Actually, transfer waves, the very important thing is that they can propagate, propagate through the solids and surface of the liquids only. Transfer waves, they do not propagate through the liquids and through the gases. The best example for a transfer wave, is what actually? Light waves. Light waves comes under transfer wave. Children, in exam, they may ask you this question. Mention the differences between longitudinal wave and transfer wave. Longitudinal wave, transfer. Children, if possible, I will try to show you on board with a, with a picture, the difference between longitudinal wave and transfer wave. Kindly just note down. So children, hope the concept of wave and the types of wave are clear, right? Fine. So now we discuss the terms related. Just we discuss the types of wave, children. Now terms are related. The terms are left like that only. Okay, now we have to discuss. Let us discuss. So the first important term, children, let us discuss amplitude. Amplitude. What is amplitude, children? So look at here. There is a reason why I didn't rub this diagram. What is amplitude, children? Children, if you can see this particle A, particle B, particle C, particle D, particle E, particle F. Among these 6 particles, which particles will have maximum displacement, children? Yes, obviously you can say that here is a particle B, and this particle B, and even here particle E. Clear? Yes. This maximum displacement only we can call it as an amplitude. Children, very clear. See, even you can take a longitudinal wave also. They are vibrating, but see children, again I am telling you, all particles may not vibrate, may not have equal displacement. Few may have maximum, few may have medium, few may have minimum, of course. But during at a certain time, every particle may achieve that maximum displacement. That is, of course, we are not going that, that discussion actually. So here, if you, especially in this diagram, children, particle B and particle E, these two will have maximum displacement. Now, if you can measure this, it might be 4 centimeter. Example, I am telling you. So this 4 centimeter only we can call it its amplitude, which means what, dear children? The maximum displacement of the particle from its mean position is called amplitude. So it's very, very important. The maximum displacement of the particle, from its mean position is called amplitude. Am I clear? Fine. So now, next, the important term. The next important term, wave. Hey, you may get one doubt actually. Sir, till now we discussed about wave. Again, why to discuss? No, just let me give you one idea actually. Of course, wave concept we discuss. But children, when you can see that one complete wave is formed. So when you can take a longitudinal wave, children, one compression, one rarefaction will give you one wave. Whereas when you take one transfer wave, children, one crest plus one trough. So one crest plus one trough, complete it is wave. So here to here, half wave. Again from here to here, one more half wave. So from complete, from children, let us say it's like a 0. Let us take it some x. So from here to here, we can call it as a one wave. So in terms of longitudinal wave, children, in terms of longitudinal wave, one compression plus one rarefaction will give you one wave. Whereas in terms of transfer wave, one crest plus one trough will give one wave. Clear? Fine. So next here, time period, children, very important. Time period. Time period will represent with a capital T. Children, here T, don't get confused. Here T means trough, here T is a time period. What is the time period, children? Again I am telling children. So to complete this wave, will it take some time? Yes, obviously. Some time will be taken to complete one wave, right? That time taken only we can call it the time period. That is the time taken to complete one wave. It might be transfer wave or it might be a longitudinal wave. That is called actually time period. Next, frequency. Next it is frequency. Frequency will represent with the small n. Some textbooks small n also we can use to represent the frequency. So children, frequency is it's a matter of number of waves produced in a second time, in 1 second. It's very, very important. So how to calculate frequency, children? The number of waves per second. Number of waves per second. So the number of produced in a second time is called what actually? Frequency. If more number of waves are produced in a given time, frequency is more. If less number of waves are produced in a given time, the frequency is less. Am I clear? Fine. And children, how time period and frequency related? It's very, very important. Even in exercise questions also, we have some numericals. The numericals based on the relation between time period and frequency are very important examination point of view. So children, here frequency is nothing but the reciprocal of time period. It's very, very, very important. Frequency is the reciprocal of the time period. Then what are the units of the frequency? Units of the frequency. Children, units of amplitude, you can measure meters or in centimeters also. So time period, yes, seconds only. So units for frequency is what, children? Per second or second inverse or SI is very important. Hertz, very, very, very important. Hertz. So representing is capital H, small z. Very, very important. Am I clear? Fine, children. So the fourth term. Next, the fifth term, most important. Wavelength. Wavelength. So the distance covered by the wave in a one time period of a particle of the wave, children, is called what actually? Wavelength. See, wavelength can be well understood in terms of transfer wave and a longitudinal wave. So in the case of longitudinal wave, children, let us take here. In the case of longitudinal wave, So during the propagation of longitudinal wave, yes, we discussed that compressions and rarefactions are formed. Am I right? Yes. So compressions will be like this, very molecules, particles of media are very close, and here is rarefactions, again compressions, again rarefaction, again here compressions. So compressions, so compression, rarefaction, compression, rarefaction, compression. So here, how to define a wavelength in terms of longitudinal wave chill? The very important. So here, what we can say, the consecutive distance between either two crust or troughs is called wavelength. Children, wavelength is a represented by a letter called lambda. Lambda. This is Greek letter lambda. How to spell it? L-A-M-B-D. Lambda. Lambda is a symbol which we use to represent a wavelength. So children, in terms of longitudinal wave, how to define the wavelength, children? The distance between the two consecutive either crust or it's not crust, compressions. Sorry, it's compression. So the consecutive distance between the two compressions or two rarefactions is called wavelength. But how to define in terms of transfer wave? Children, let me erase this so that we will have enough space to discuss. So fine. So here, how will represent the transfer wave, children? Actually, so transfer wave is like this, right? It's a wave propagating. So this is a crust, trough, crust, trough, crust, again trough it is. So you can take either two successive crust or two successive trough is called lambda. This is very important. So in examination you can write either of one. What is a wavelength, children? The distance between two consecutive either compressions or rarefactions is called longitudinal wave, or in terms of transfer wave, the distance between two consecutive crusts or troughs is called wavelength. Am I clear, children? So as it is a wavelength, you can measure in terms of meters and centimeters. It can be used because it's a distance only, right? So this is what actually wavelength is. Fine. And the next term is, children, very important, wave velocity. Wave velocity. What is wave velocity, children? The distance covered by the wave in a given time, in a second time, in a 1 second. The distance covered by the wave in a 1 second is called what actual wave velocity. So wave velocity can be represented with the letter V. So the very important thing is that wave velocity can be differ from medium to medium. If the wave is moving from air to glass to water, definitely wave velocity will differ. So here wave velocity depends on the density of the medium. Wave velocity depends on the density of the medium. Very important. So children, these are the terms. Amplitude. What is amplitude? The maximum displacement of the particle from its mean position is called amplitude. What is when you consider one wave is formed completely, so it's the one compression plus one rarefaction will give you one wave, or one crust plus one trough will give you one wave. Okay, fine. Now what is the time period? The time taken to complete one wave is called time period. Now what is the frequency? The number of waves produced or made, okay, in 1 second is called what actually frequency. And here wavelength means, of course, just we have seen in terms of longitudinal wave, in terms of transfer wave. So in the examination point of view, the relation between wave velocity, wavelength and frequency in a time period is very important. Examination point of view, the relation between wave velocity, wavelength and this time period, of course even frequency also. So children, in the simple terms, let us think, what is speed is equal to? Speed is equal to what, children? We know that speed is equal to distance by time. Speed is equal to distance by time. Speed is equal to distance by time, children. So speed will represent with the letter V. Distance what, children? Wavelength. When a distance is a wavelength, then time will become a time period. Why? Because the wavelength is a distance traveled by the wave in one complete time period of a particle of the medium is called what actually wavelength. When distance is lambda, then time period will be t. So V is equal to lambda by t. But children, We know that frequency is equal to 1 by time period. So here 1 by time period we can write as a frequency. So V is equal to frequency into lambda. Children, very important examination point of view. So examination point of view, this formula and this formula are very important. Based on these two formulas, we have a very simple numericals which will be asked in an examination. Okay children, so these are the terms related to the wave. So children, before going to discuss the speed of the sound in a different mediums, let us come back to the propagation of sound, children. Let us come back to the propagation of sound. Children, in a textbook, propagation of sound is discussed first, then wave concept. But children, I feel that, without understanding the wave concept, how sound can propagate, it's, of course, some people can understand, but I feel that it is better first you learn about the wave concept, then come back to the propagation of sound, so that, it will become very easy to us to understand. Okay, now fine children. Now children, let us take that here. So it is completely air. Of course, obviously, we are in atmosphere, there completely air is there. So let us take example where it is. Let us take here is one bell. It's not a school bell. It might be in temples, it will be there. During the examination, many of us will get that, we'll go to the temples, we'll go to masjids, church, and we'll pray to the God, I should get a good mark. Whether I read or not, whether I can understand or not, but I should get mark, I don't know. So you give me a mark, I'll offer something. It became like a, it's like a business deal. God, you give me marks, I'll give you something. Okay, now fine. Yes, let us take here is some bell, children. So the moment when a bell is hit, children, what happens? We can hear the sound. No doubt about it there actually. But children, the moment when you can hit that bell, it start vibrating. This is what actually we discussed beginning of the session. Vibrating bodies only can produce sound. That we can hear, right? Yes. So let us take here some person is there here. Some person, let us take. So here is some person. One person. Okay, we are not sure. Something. Person, let us take that. So here, for us, the ear is important, not figure here. Okay. So here, what happens? When this here it is hit, actually, the person can hear that sound actually. But what actually happening? Let us see in detail, children. Children, around this, what will be there? Air is there. Here, complete. This is complete, here air is there, no doubt about it, it's completely air is there. Means here, air is a medium. In this medium, what will be there? Obviously, molecules will be there. So, the moment when this bell start vibrating, then what will happen, children? These vibrating body, let us take here some molecules are there in between. Let us say some air molecules are there. Air molecules. Then what will happen here? So it will be vibrating like this, to and fro, which we discussed. It is a to and fro it will be discussed. Means what here? It will give a push. So what will happen? These all molecules will come closer. Again, these molecules will push other molecules. These molecules will push other molecules. So this is how that push is carried. Push is what? The energy. The vibrating body is disturbing the medium where it is vibrated. It is just disturbing the molecule. Disturbing the molecule means what? It is giving the energy. That energy is transferred. Children, the moment, just for a while you think that the bell is in this position, just right side. Then left side, what will happen? There will here molecules mean there will be a some maximum distance among the molecules. Here all molecules will come close to each other, and these molecules, they don't move. These molecules will push. Means after some time these will move a bit far from each other. So like this, what will happen as we discuss about a longitudinal wave, children? These here compressions and rarefactions are found. Compression, rarefaction, compression, rarefaction, compression, rarefaction, compression. So this disturbance, whatever is carried in the form of compression, rarefaction, finally it will reach the ear. That is what eardrum. And this disturbance will disturb the eardrum. and accordingly our eardrum also starts vibrating. Those vibrations are sent to the brain in the form of electric pulses where the decoding will take place, and we can understand that disturbance, that sound we can understand. So here as this sound is traveling, so what happened? Compressions, rarefaction are formed. That's what children, in air sound can travel in the form of longitudinal wave, which means what? As the sound is propagating in the air, children, compressions, rarefactions formed. Children, again I'm telling you, if you want to understand this, let us recall what we discussed for longitudinal wave. The best example which we have discussed, where the persons are standing in a queue, how the push is carried to the front and the back. That is what exactly happens. Am I clear? So these are the regions of a maximum maximum density and pressure, and these are the regions where low density, low pressure. The regions of high pressure, high density is called compressions. The regions of low pressure, low densities are called what actually? Rarefactions. So this is how actually sound can propagate in the air only, children. Here I am specially talking about air only. As per the syllabus also, we have the propagation of sound through the air only, not air only. Clear? Just copy this so that we'll move to the speed of the sound in different mediums. Clear? Fine. Children, examination point of view, the most important concept is what? Concept is speed of the sound in a different mediums. But before that, we forgot a small important thing, a small only, but sometimes students are getting confused. What is that? Representation of wave, children. This is very, very important. So the wave can be represented in terms of displacement distance and displacement time also. Let us see, children. Displacement, two graphs are there we have. Displacement. Children, here don't have a confusion. Few children, they will have a confusion. So I think some of you may think that I am representing two transverse. No, it's not that actually. So displacement time graph and displacement distance graph. So before that, children, I want to give you one clarity. Some of you may have a confusion. Sir, displacement distance in a motion 1D, we discussed that displacement distance almost same, something like that. Children, it's very important. Here, what is the displacement, what is the distance, we need to understand. Let me give you clarity. Children, this is how actually wave is propagating. So this is what actually distance covered by the wave. Children, try to answer, very, very important. This is how distance covered by the wave. Displacement means what actually? Particles in the medium, they vibrate up and down. This is a displacement. So this is a displacement. This is a distance. Distance for a wave, distance of wave, displacement of a particle. Try to answer, very, very, this clarity is needed here. Distance covered by the wave, displacement achieved by the particle. Displacement achieved by the particle. Hope I am clear? Fine. So children, in these two waves, one common thing is there. What is the common thing? On y-axis, displacement is taken. So children, the displacement of the particle from its mean position, this only we can call it as an amplitude. So either it is a displacement time graph or a displacement distance graph. In both cases, yes, this is an amplitude. But the difference is that, children, here in a displacement time graph, time is taken x-axis. So this will give you time period. This will give you time, very, very, very important. So, but whereas here, this distance is not time period here. This distance, this is what actually wavelength, children, very, 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 very important. This is what actually, where some students are getting confused. So you should see. So in examination, how the question will be given, children. They will give you displacement time distance graph. Here some letter P is given. Here letter Q is given. They will ask you to identify the letter P and Q and define. Here some Q is given. So you can't say that is a time period. No, you have to see either the displacement distance graph or displacement time graph, children. And displacement distance graph, we can represent amplitude and wavelength. But whereas on displacement time graph, we can represent amplitude and time period. In both graphs, the common thing is what actually amplitude is a common thing. Difference is what here? If it is a displacement distance graph, we can represent the wavelength. Whereas here, we can represent the time period. Is that clear? Fine. Now come to the last Since 10 minutes I have been telling you that next we are going to discuss the speed of the sound in a different mediums, right? Yes. Now children, I am sure that we have come to that concept. Speed of the sound in a different mediums. Let us see. Very, very important. Speed of the sound. Speed of sound. Speed of sound in different mediums. In a different medium. Children, as I said that here medium, very, very important. So there should be some, I said when I said about the agenda, there one point I highlighted, the properties of the medium through which sound is traveling, which I said that we are going to discuss. So very, very important, children. So the sound through which, the medium through which it is traveling, that particular medium should have three important properties. Very, very important. Very, very important properties, children. Very, very important. Just note down this. Very, very important. The properties of the medium. The properties of the medium. So first, children, the medium should have elastic in nature. Elastic in nature. So why a medium should have elastic in nature? Children, very clearly I said what. So when I discussed the propagation of wave, children, I said that particles of the medium, they do not move, rather they will vibrate from their main positions. I said there only we have taken example of students who are sitting in a row, who are passing on an object. I said there what happens, just recall, the student is like a turning back, coming, turning back, coming. Children, it happens only when we have this elastic nature. Our body has that elasticity, children. Otherwise, if you are bending, again we are coming up, means what? Our body is bending. It's elasticity a little bit. Again, it's coming back to the, see what is the elasticity? Regaining the original shape and size. Regaining the original shape and size. So as a medium must have elastic nature, so that particles, when they will vibrate, again they will come back to their original position, again they will vibrate. They will come back to their original position, again they will vibrate. So medium must have elastic in nature. And the second one, children, medium should have inertia. Medium should have inertia. Why a medium should have inertia means, children, wave means what actually? One of the modes of transfer of energy. When, see, to transfer the energy for a while, the molecules, they should trap the energy, right? Energy must be trapped. Energy must be stored within the molecules. That's very, very important. Why energy must be stored? Because wave is nothing but the propagation of energy only. For that, medium should have inertia. And the third important thing is that medium should be a frictionless. Medium should be a frictionless. What if friction? Medium has a friction. Children, whenever there is a presence of friction, there will be a loss of energy. That we discussed in a loss of motion. Of course, whenever there is a friction. But till date, there is a big question. Is it a good one or a bad one? Yes, it depends on situation. Friction is a good and as well as bad also. But for our case, especially in this case, children, the medium should be a frictionless, so that there won't be energy, there won't be any energy losses. Is that clear, children? Yes. So what are the three properties of the medium medium should possess, so that the sound wave can propagate easily? It's very, very important. The medium should have these three properties, children. Medium should be elastic in nature, and medium should have inertia, and a medium should be a frictionless. Is that clear? Fine, children. So children, here the speed of the sound in a medium depends on two factors, children. Very, very important. The speed of sound in a medium depends on two factors. The first one is elasticity, and the second one is density. So elasticity will represent with the letter E, and the density will represent with the letter O. So here we can write V is equal to E by rho. Children, here rho is called modulus of elasticity, or elasticity modulus also we can call. E is called here modulus of elasticity. Modulus of elasticity. Children, regarding this modulus of elasticity, you will be learning in a +1 in detail, even not even 10th class also. In +1 only, there you will have a chapter name called, mechanical properties of solids. There in detail it will be discussed. So when if the medium is, if it is a solid, children, for solids, this modulus of elasticity only we can call it as a Young's modulus means for solids this equation V will become Y by rho. So whereas for liquids, so this modulus of elasticity only we can call it the bulk modulus. That is bulk modulus by density we can write. So this is what actually very important, children. The speed of the sound in a medium depends on two factors. One is elasticity, another is density. But children, again here one important point regarding speed of sound. So the scientists who took initiation to calculate the speed of the sound in air is actually Sir Isaac Newton again. Children, very important. So it means here we have Newton equation, again we have a Laplace equation. So examination point of view, just you can remember, numericals won't be asked. Some of you again may have confusion, sir, what is this modulus of elasticity, Young's modulus, bulk modulus, just you leave it, just keep in your mind. If not, just you leave it. It's not a matter, because this is important for a +1, not for just remembering the formulas and what are the terms, what we can call E, what we can call rho, that is enough. So regarding speed of the sound, children, the first scientist who took initiation to discuss is actually Newton. And the very important thing is that, so Newton assumed that when the sound is traveling in the air, he thought that it is a isothermal process. He thought that the propagation of sound, is what actually it's is nothing but the isothermal process. He thought isothermal. Children, it's very important term. It is isothermal process. What is isothermal process? The process in which temperature remains constant. Temperature remains constant is called actually isothermal process. Means he thought that when the sound is propagating, the temperature of the medium remains constant, he thought actually. And children, in isothermal process, modulus of elasticity is nothing but the pressure, that is E is equal to P. So in the place of E, if you can substitute P, V is equal to square root of, children, don't get confused, this is P, this is rho. What is the difference? P is standing, rho is what? Bit bending like this, a little bit bending, right? So it is a V is equal to P by rho. Children, what is the P value? At a normal atmospheric conditions, P is, we know that 1.013 into 10 power 5 Newton per meter square. And what is the density of the air? It is 1.3 kg per meter cube. 1.3 kg per meter cube. If you can substitute the values and if you can calculate, you will get approximately 280 meter per second we are getting. But children, here problem is that actually the experimentally the speed of the sound in air, especially the speed of the sound in air is calculated as 330 meter per second. 330 meter per second. So this is not accepted. Then one more scientist, the name called one more scientist, hope I can erase this. Yes, it's called Laplace, children. One more scientist, who is that? He is a Laplace. The scientist name called actually Laplace. So he came forward. So he assumed that, children, the propagation of sound in air is just because of it's due to the adiabatic process. He said adiabatic process. Children, definitely these terms, isothermal, adiabatic, these terms in intermediate first year you are going to learn, where you will be learning in thermodynamics. In thermodynamics, you will be learning about a isothermal process and adiabatic process. Just you remember, what is isothermal process? The process in which temperature remains constant. What is adiabatic process? The process in which heat remains constant, but temperature changes, he said. Means He did not do any new things, children. Just he made some corrections for a Newton's equation only. And in an adiabatic process, elastic modulus of elasticity is equal to the gamma into P. What is this gamma, children, again? So here is gamma is called the ratio of specific heat capacity at a constant pressure at a constant volume. Don't get confused. No, in examination for a 9th class, they don't ask you what is gamma and everything. Just remember, for air, children, approximately gamma value might be 1.3. Approximately we will take. Okay. So in the place of E, just substitute gamma P. So V is equal to square root of gamma P. It is, I think it is 1.4. Sorry, 1.4 by rho. That is the density. So children, if you can substitute gamma value 1.4. P is as usual 1.013 10 power 5 and the rho is 1.3. If you can substitute, approximately we are getting 330.21 meter per second. So this is almost matching with the experimental value. Children, don't get confused about this elasticity modulus, Young's modulus, adiabatic process, isothermal process. In a 9th class exam, they don't ask you what is adiabatic process, what is isothermal. Just remember these formulas. And moreover, no numericals will be asked based on these formulas also. No need to get confused. Just for sake of your idea. Now we should have a little bit idea so that in intermediate first year, we will get a full clarity. Okay, children, just copy it. Now we discuss the factors on which speed of sound in air depends. Children, now we will be discussing the factors on which speed of sound depends. Speed of sound depends. So I think, children, as we are discussing bit slow, the video might be a lengthy, but no problem, children. Have patience. Just watch. If possible, just pause it, take a rest, come back again, watch it. You know, by saying one short video, I cannot jump and I cannot skip a topics, because at least few people may depend on our video. If I can skip the topics, what will happen, it's like not doing like justice to students, right? Fine, children. Now, speed of sound depends. Children, very, very important. Speed of sound depends. First one, children. So let us take out the formula. V is equal to what we can say? Yes, pressure by gamma P by rho, right? Yeah, finally we got gamma P by rho. So children, the first one is density. Children, the very important thing is that here speed of the sound is inversely proportional to the square root of the density. I mean what? More the density, less the speed of the sound. Less the density, more the speed of the sound. Children, did you remember just the beginning of this session, I asked you one question. Which air has more density? Wet air or dry air? Now that point is very important here. Now let us see first of all, what is a dry air, what is a wet air? Some of you may think, sir, is that much important? So wet air, dry air, children, it is not like a wet cloth and a dry cloth. So much of difference is there. Let me tell you, children. Let us take here a given volume. Two identical volumes I have taken. Okay, fine. And here total I have taken many molecules. 9 air molecules I have taken. 9 air molecule. And here also 9 air molecules I have taken. Try to understand. Very, very, very important. It may take 2 to 3 minutes time to discuss, to understand, to explain, but have patience. I'm promising you that definitely 100% you will understand. Now children, now let us take here 9 molecules. That is, mass is same in a given volume. So here density is same, density of air is same. Now children, first you think, what is a wet air? Wet air means what? Some water molecules will come into that air. Am I right? Yes. Let us say that, children, here some water molecules are coming and occupying the space of this air molecule. Let us say it's a air molecule. Let us say it. Now, children, again I am telling you, these black ones are air molecule, whereas this red color ones are what? Water molecules. Water molecules. Now children, now you tell me which one is the wet air, which one is the dry air. It's very clear. It is dry air. It is wet air. Wet air. Children, density means what? Density means mass per volume. Now children, now you think in this two, in which case more number of air molecules are present. More number of air molecules, more mass. Less number of air molecules, less mass. So now you think, in which case more number of air molecules are present? In a dry air. In which case less number of air molecules are there? In wet air. Now children, in a dry air, more number of air molecules are present. So more is a mass, more is a mass, more is a density. More is a density. Very, very important. That's what I asked, air density. The density of wet air or dry air. So now you tell me children, just you think, in this number of air molecules are less, so the mass of the air is less, the density of the air is less. So children, the density of the dry air is more than that of the density of the wet air. So it's very, very important. Very, very important. I am talking about a density here. Density means what? Mass. See, for a given volume, you think about the mass here. Here more number of air molecules are there. More mass, obviously more density. Clear? Fine. Why I am saying? Because this important examination is a very, very important point. Now children, speed of the sound is inversely proportional to the density. Speed of the sound is inversely proportional to density. Now you tell me, in which air speed will travel faster? So where the density is less, there speed of the sound is more. Obviously, in a wet air, speed of the sound is more. Why? Density is less. Less the density, more the speed. More the speed, more the density, less the speed. So am I clear? Clear? Fine children. It's very, very important. So here, first term is the density. So speed of the sound is inversely proportional to density. In which air speed of the sound is faster? Obviously, wet air only. Okay, fine. Now second one is children, temperature. Second one is temperature. Children, speed of the sound in air increases with the temperature. Experimentally, it has been proved that here, speed of the sound is directly proportional to the square root of the temperature. Square root of the temperature. Children, for every 1 degree Celsius rise in temperature, the speed of the sound is increased by 0.61 meter per second. Children, very, very important. For every 1 degree Celsius rise in temperature, the speed of the sound is increased by 0.61 meter per second. Example, I'll tell you. Example. For example, children, at a 27 degree Celsius, the speed of the sound is 330 meter per second. Children, for just example, I'm taking, not exactly. Now, temperature is increased to 28 degrees Celsius. Then what will be the speed of the sound? It will be 330.61 meter per second. That's what I said, that the speed of the sound is increased. For every 1 degree Celsius rise in temperature, the speed of the sound is increased by 0.61 meter per second. Clear? Fine. And children, the third factor is humidity. The third factor is humidity. Children, again here we need to understand the density of the air only, children. See, the very important thing, children, if humidity is increased, density of air, children, humidity is increased means what? Amount of water molecule increases, means air molecule decreases, means what? Density of air decreases. Density of air decreases, children, very, very important. As density of air decreases, speed of the sound increases. So that's what? The speed of the sound is proportional. It increases with the density. Means sound will travel faster in humid air. Clear? Fine. The fourth one, children, the direction of wind. So it's very, very important. Look at here. For example, here listener. Here is a listener. So, children, hope I can erase this. Hope you have copied. Yes. Let me tell you. And here is speaker, let us say. Speaker. When he is speaking, children, obviously, sound will travel. Sound will travel in this direction. No doubt. Sound will travel in this direction. Children, for example, this is the, let us say, it's the speed of the sound Vs. If wind also blowing in this direction only, then what will happen, you know, the speed will be added. The speed will be added, means the resultant speed will become Vs plus Vw, so that the speed can travel faster. If the, you know, if the speed of this, the direction of sound and the direction of wind both are in the same direction, they will be added, so that in result the speed will, the sound will travel faster. If the sound is traveling, the air is blowing in this direction. If air is blowing in this direction, let us say that, then what will happen, children? In this case here, it will be subtracted. I mean what? Sound is trying to travel in this direction, but the wind is blowing if in this direction. In result, what will happen? Sound may not travel faster. Then the speed of the sound will become less than that of in the first case. So, if the sound is traveling in the direction of the wind, then it will be more, it will be increased. If the sound is traveling in opposite direction of the wind direction, then it will be, the speed of the sound will be decreased. Clear? So children, these are the 4 important factors on which speed of the sound in air, the speed of the sound in air depends. Can I erase? Fine. Now children, we will see the the factors on which speed of the sound in air. Children, here I should write here, it is in air only, strictly. In air does not depend. So the first factor is pressure. Definitely with this many students will get confused. Pressure. Why? Sir, because V is equal to, it is gamma P by rho. Sir, in this formula pressure is there, but you are saying that speed of the sound does not depend on pressure. Yes children, let me tell you. For example children, just wait a second. So yes, for example, let us take it is an object. Here I don't have a duster. Okay, fine. So it is an object, children. Let me increase the pressure. If I increase the pressure on this, children, what will happen? The molecules of the cloth will come closer to each other. Means, is the density increasing or decreasing? When I increase the pressure on this cloth, all the molecules of the cloth are coming closer, which means what? Density is increasing. So it's very, very important. Means, when we increase the pressure, density increases. When we decrease the pressure, density decreases. Children, it's a very important point. Look at here. When you increase the pressure, means with the pressure, density increases. Which means what? If pressure is increased by 3 times, density also increased by 3 times only. Then look at here. V is equal to square root of gamma 3 P by 3 rho. 3 get cancelled. Again it will be gamma P by rho only. Is there any change, children? No. Which means what here? P by rho ratio is always constant. So whether you increase the pressure, you decrease the pressure, so the speed of the sound doesn't change. It's very, very important. Why? Because with the pressure, density increases. When you decrease the pressure, density of the air also decreases. Which means what? P by rho ratio is always remains constant. Okay, fine. Yes, children. Even amplitude, children, very important. Amplitude, it does not depend on the amplitude. And third one, wavelength or frequency. It does not depend on the wavelength or frequency. That is what, either infrasonics or ultrasonics, children. Any sound you can take, any type of sound in a given medium, they will travel with the same speed only. It's not, it doesn't depend on the what we can say, frequency. So children, so these are the factors on which speed of the sound in air does not depend. Okay, fine. Now children, let us see the comparison between the sound waves and the light waves. Just one or two comparison we'll see. That much depth we don't go. Just one or two comparisons children. So here sound waves for us is important as per the syllabus. I mean as the chapter is sound, we have to highlight this. So sound and light children, the very important thing children. So here sound cannot travel through vacuum. Am I right? Yes. Cannot travel through vacuum. But children, light can travel. Light can travel. So sound belongs to the longitudinal wave. Longitudinal wave. But whereas light comes under transverse wave. Transverse wave. Okay. And basically children, sound is a mechanical. It's a mechanical wave. Actually children, here mechanical wave means what? The wave which requires a medium to propagate. Obviously for a sound medium is required. So whereas light belongs to the electromagnetic radiation. Electromagnetic wave, right? It is a electromagnetic wave. Electromagnetic wave it is. And children, the speed, if you can see in different mediums, the speed of sound is more in solids, next in liquids, next in gases. But light is completely different. The speed of light is more in gases than liquids, least in solids. So children, in examination also it's very important. They will ask you to write the differences between a sound and a light, or they may ask you to compare the sound and a light. Clear? Fine children. And the last topic, I think this topic is discussed in a unit B, which we are going to cover children. So come back to the, again a same question, how the sound is produced? Children, sound is produced with vibrating bodies. Can we hear the sound produced by all vibrating bodies? Means no. We cannot hear the sounds produced by vibrating bodies. This is very, very important. Okay, now fine. So children, here based on what we are going to differentiate the sounds actually, based on the frequencies children. So children, the sound with a frequency less than 20 hertz are called infrasonics, whereas the sound between 20 hertz to 20,000 hertz, we also can write 20 kHz. These are called here sonic sounds. These are called actually sonic sound, or we can say it's an audible range also. This is sonic sounds, or we can say simply it's a audible range. It is audible range. Fine. And the sounds with greater than 20,000 hertz, that is 20 kHz, greater than 20,000 hertz are called ultrasonics. This is called ultrasonics. Ultrasonics. Still very, very important. So here, any sound with less than 20 hertz frequency is called infrasonics, which we can't hear children. Whereas the sounds with a frequency range greater than 20 hertz, 20,000 hertz are called ultrasonics, can't be heard. Only children, the sounds between the range between 20 hertz to 20,000 hertz, the sounds between the frequency range between 20 hertz to 20,000 hertz only can be heard. This is very, very important. And children, the important, the very, very important point here is that if you can see elephants children, elephants and whales children, the very, very important thing is that these can produce infrasonics. Very, very important. So we should not underestimate the animals. And one more thing children, a very important thing is that here dogs can hear the sound up to 50,000 hertz, and whereas if you can take a case of bats, bats can hear the sounds up to 100 kilohertz, whereas the dolphins children, very important, dolphins can hear the sounds up to 150 kilohertz, children. So mind blowing. So sometimes we think that we are the human beings or the too intelligent and all these things, but we cannot hear the sounds with less than 20 hertz and greater than 20,000 hertz, but animals can. So let us not underestimate animals, children. So either it's an animal or human being, everyone has their own importance, and everyone has their own talent, we can say that. Okay, now fine. So this is a very important. Now children, here the examination point of view, ultrasonics are very important. So because we will find many applications with the ultrasonics. Why we will find? Because of their special properties. So what are the special properties of the ultrasonics is very important. So the first thing is, the children, the first important property of ultrasonics is a high directivity. It's a high directivity. And the second property is that high energetic. It's a high energetic, very important. High energetic, which means what? They can travel a long distance without getting deviated, without getting absorbed by the medium, children. Without getting absorbed by the medium. When compared with other sounds, these sounds can't be absorbed much actually. So for that reason only, we will find many applications. The first application, exam they may ask you to write the applications of ultrasonics, children. So first one is, we can use in a sonar. What is sonar, children? Sound navigation and ranging. It is a method to find the depth of an object, under the water, even to find the depth of the sea, where we can use ultrasonics. Of course, echo concept is involved. So that echo concept we will be discussing in a 10th class. Just you remember now, in sonar, we can use ultrasonics. And the second one thing, bats, very important. Bats can produce ultrasonics for what? To move from one point to another point, so that they can identify the obstacles in between. So they will produce ultrasonics, so that these ultrasonic sounds will get reflected back, and that can be heard by the bats. What is genius? Actually, bats are the real genius, I can say that. Okay, na? Because though they don't have eyes to see, but with just producing ultrasonics only, they will be moving here and there. Ultrasonics. Okay, now fine. And here, it is also used in what we can say, children, ultrasound scanning. We can use ultrasound scanning. Ultrasound scanning means to see the inner organs. So if there is any problem of a liver or any intestine, if any problem is there, even children, to see the growth of the mother's womb. To see the growth of the baby in a mother's womb also, we can use this technique only. Even we can use ultrasonic sounds, to see the, function of the heart also. It's very important. Okay, fine. And even these ultrasonics, are used to break the stones in the kidneys. Hey, not to break the kidneys, stones. Stones means don't expect the big stones in the kidneys. Not that, very small stones will be there. So without surgery also, if you want to just remove that, so it's not possible to remove. So those stones which are present in a kidneys, they will be broken and will be made into small particles, and they'll be left in a wastage only. Clear? Fine, children. So these are the properties of ultrasonics and the applications. So children, so these are the topics of sound chapter. Hopefully we covered almost all we covered. Children, once again I'm telling you, in a textbook the order might be different, but the order which we discuss might be different. Not to worry. Just I wanted to take in a proper sequence. So that is the reason why we have taken. Of course, you can follow that also. I'm not saying that the order of textbook is wrong, right. It's not that. It's a comfort. For me, it's a comfort to discuss. For you, it might be comfort. It's up to you. It is. So the thing is that we should not get deviated. So children, once again, I'm telling you, reading textbook is a mandatory. Whether you watch this video or not, the second thing, but give first priority for the textbook. Go through the textbook before watching the video or after watching the video. It's up to you. is up to you. It's a better before, it's up to you, but reading the textbook is a mandatory. After that, you go through the questions which are given exercise also. So children, if possible, maximum, I'll try to make the, exercises also, like chapter wise, just I'll try to make, so that students who are following a channel, for those people during the examination point, examination time, it become a bit easy to revise and everything. Okay children, hope this video is useful to you all. Thank you so much. All the very best.